Welcome, physics friends, to 16.3, which is the last unit in the light chapter, and it's about polarization. Maybe you've heard of polarized sunglasses, or if you do a lot of stuff with cameras, you've heard about polarizing filter. Today we're going to talk about what is a polarizing filter, what is polarized light, and what are some really neat ways that we kind of utilize this. So this is a picture from your book that you're seeing on the screen right here that talks about it's just kind of a little graphic of a polarized filter. So rather than showing you this, I've got a couple videos I wanted to show you that kind of demonstrate a little bit better how polarization works. I want to start off right here with a professor from UCLA.
Now, you might be wondering, is light a transverse or a longitudinal wave? How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way,
This is really neat how this works.
no matter what crazy wave I send, only the left and right components get through.
Only left and right components. So when you go at a diagonal, the X component goes through, but the Y component gets canceled.
It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right.
Now these are polarizing films. These are what you make sunglasses out of.
When these two are crossed, we get absolute darkness, zero transmittance.
So just like imagine that fence that he had before, one going left and right and another fence, one going up and down. When you put those together, they make like a crosshatch and nothing gets through. You rotate those so where they line up and you'll get 50% through.
But if we cross them the other way, light still gets through. They're polarizing together the same way.
Not neat? Kind of opening, it's like instant shades. I did a quick Google search. I just typed in polarization of light, so you can kind of see the whole fence analogy right here. The two fences aligned, the light can get through. The fence is at 90 degrees from other, they don't go through. You'll see a clock here. I'm going to take you to a friend of mine. His name is Bill Hammock. He's a chemical engineering professor down at the University of Illinois. And he takes apart an LCD screen like your iPhone, your laptop, the screen that you're looking at right now, your TV screen. How does that use polarization? And I just typed, you click on the filter here, and to kind of look at whenever light bounces off a flat surface, it becomes polarized. So looking at, this is why fishermen wear polarizing glasses, because if you look, you orient your glasses like this, so the light coming off the surface of the water gets blocked by that. So then you can actually see down into the water. So here you can see into the water, see fish. Here you wouldn't, the glare. An example of a cell phone, see how it's cutting that glare? This is a lot the same reason why people that are driving will wear polarizing glasses, because that reflections off of people's windshields in cars are cut by those polarizing filters. We use them in photography a lot too, because a lot of the light coming from the sky is polarized. I think it's polarized circularly, which is something a little bit different. Let's see if there's anything else. Oh, here's the windshield, the glare being cut by the polarizing filter. Alright, let's go back. There's one more video I want to show you. Oh, also, 3D glasses. When you go to, if you guys go to a movie where it's 3D, that's how they do that. They give you glasses that are polarized in one direction. One of the directions is one of your eyes is polarized this way, the other eye is polarized that way, and what they do is they broadcast two polarized screen videos on the screen at once, so this eye cuts out the polarized image that's left and right, and then this eye cuts out the polarized image that's up and down, so each eye gets its own separate image, and your brain puts it together as something stereoscopic. Like if I were to look at my finger really close up, I have to keep my eyes in or look out. So you have two separate images that your brain's putting together because of your two stereoscopic eyes. Let's see how your LCD screen works.
This monitor uses liquid crystals to display images. How this thing works amazes me. Let me show you. Let's start at the back of the screen. If you look here, you'll see a row of LED lights at the bottom called the backlight. These are the only lights in the monitor. Next, I'll put in what's called the optical system, which makes the light even across the back of the screen. Now, the first sheet makes a nice, even white background for the light. The next piece is called a light guide plate. You can see it's covered with dots. When light enters from the bottom edge, it propagates down the plate by total internal reflection, unless it hits one of the dots. And they make some of the light rays emerge out of the front. Then engineers place a diffuser film. It helps eliminate the
We'll
dot
talk about
pattern
total
from the
internal
light guide
reflection
plate.
next chapter.
Then comes a prism film. You can notice here that where I have the sheet, it's much brighter than where it isn't. So at this point, if we put the last diffuser film on, we have a very evenly lit surface, all from a single row of LED lights at the bottom.
So all those sheets, all they did, they just evenly lit the bottom of the back of the screen. They call it the backlight.
The backlights are always on, but what controls what we see is this piece of glass. It functions as a shutter. At the back and front of the sheet are two polarizers. They stick tightly to the piece of glass, but let me illustrate it with two sheets that I have. If I lay this sheet on the optical system, you can see that it passes light. And if I put this piece on top, it also allows light to pass. But if I rotate it exactly 90 degrees to the bottom sheet, you'll see the light disappears. The bottom sheet creates polarized light, which will only pass through another polarizer set to the right angle. Now, of course, in this LCD monitor, the front polarizer doesn't rotate. Other than the on-off switch, the monitor has no moving parts. Instead, what we do is we place these two polarizers 90 degrees to each other, this configuration that allows no light through. And then, if we want light to pass, we twist the light within the glass pane to match the front polarizer. How? Well, it's the simple-looking piece of glass that does all the magic. Let me put it back on, and you can see that the image reappears. I just love that. It's actually a sandwich of glass. Engineers fill the space between the panes with tiny glass beads to keep them separated, and with organic molecules known as liquid crystals. The crystals have interesting properties in that they do not allow light to pass uniformly along both axes. Grooves are formed on the surface of both pieces of glass at 90 degrees to each other. The molecules in between line up in a beautiful helix. When light from the backlight passes through the first polarizer and enters the sandwich, it's rotated by the liquid crystals so as to allow it to pass through the second polarizer and emerge out the front of the screen. This is known as the normally white mode.
So here's your two polarizing filters. Here's an up-down polarizing filter. Here's a left-right, and normally light won't go through that. But you have these liquid crystals that when they're left alone, they form this helix, which actually twists the light 90 degrees, which allows the light to go through. And that's why they call it the normally white, because light's going through. The white light from the backlight can pass through and be open and on.
Applying an electric field across a sandwich causes the crystals to line up lengthwise. Now, the light that passes through the front polarizer is not rotated by the crystals and can no longer pass through the front of the screen. We call this the normally black mode. Now that we can control the...
Now, this is what your contrast ratio is on your TV. The amount of light between all the way black, because monitors can't turn off all the light. Some of it still seeps through. So if you've got a really good TV monitor, its black is black and its white is white, are as far apart as possible, and that gives you a huge color dynamic, which we call contrast ratio.
Light through the glass. How do we get color? Let's look in detail at the piece of glass. By controlling the voltage between these transparent electrodes, we can control the intensity of the light that passes through. Now, there's much more to the glass plate. Let's examine this section where my sleeve meets the gold background. If we zoom in, you can see it's made of pixels. If I turn off the image and backlight the glass sandwich, you can see the screen contains red, green, and blue sections. These are subpixels. The three together make a single pixel. In the sandwich, they are simply colored tiles that overlay the front transparent electrodes. They follow the RGB color model. We adjust the electrode shutter behind the subpixels so that they make up a particular color. For example, to get the color of the blue in my shirt, we set the red subpixel to 12% of maximum intensity, green to 21%, and blue to about 50%. And now for the last critical piece in the glass sandwich. On the back pane, engineers paint tiny devices called thin film transistors. That's why these monitors are often labeled TFT. Each subpixel has a transistor which controls it. This transistor you see here functions as a switch that allows the screen to be updated row by row. By applying a voltage to a specific row while keeping the other rows grounded, we allow each subpixel in that row to receive video data coming from the top of the screen. Only one row can receive information at a time, but the speed with which this happens for each row is so fast that your brain blends it into a fluid image.
Now, this is how 1080p works, because the P stands for progressive. The video updates the top row, then the next row, and then row 3, and then row 4, and then row 5, and it goes from top to bottom as fast as it can. Now, if you're watching something that's really like quick image, like sports or an action movie where things are changing on the screen quite a bit, by the time it gets to the bottom, the image has changed. So you have to, they've invented what's called 1080i. And that's where it does every other row. So it'll do row 1, 3, 5, 7, then it'll go back and do 2, 4, 6, 8. Now you can get a 1080p if you can update it quick enough, and that's where the frequency, like some you'll see that, oh, my refresh rate is 60 hertz versus 120 hertz. 120 hertz means that it refreshes the screen 120 times per second. So the faster you can refresh it, the better that it is. Now, 1080 stands for how many rows there are. There's literally 1,080 rows of pixels. If you've got a 720, there's 720, and if you're in 4K, 4K is the new thing that's coming out that you'll see in the years to come, where there's literally 4,000 pixels, 4 times the amount as 1080.
What an amazing device, and also the technology that allowed computing to go mobile. Imagine laptops, cell phones, and tablets without lightweight screens. I'm Bill Hammack, the Engineer Guy.
Absolutely. He says it right.